Okay, today I'm going to talk about Bode Plots. Start with a motivation with a simple example of a simple single pole RC filter. Then go into common terms you'll encounter and how to plot them. Get into a more complex example and then show you can prove it with Matlab. So to start, we're going to have a simple RC low pass filter here. And the reason I'm starting with this is it's actually pretty important. In real life, R could be the output impedance of some stage, and C could be the parasitic capacitance loading the input of the next stage. So the simple RC filter actually comes up a lot. And if we do voltage division to try to find the transfer function of the output over the input, we can see that the impedance of the capacitor is 1 over j omega c. Here we're going to say that S is j omega, because for electrical circuits, our input is purely sinusoidal. And of course, the impedance of the resistor is not frequency dependent, so it's just R. And here's our voltage division equation. Here we go here. We'll simplify, multiply numerator and denominator by 1, or by SC rather, which is 1. And we'll get this here. And if we simplify RC is 1 over omega naught, we'll see how that'll help us in our analysis later down the line. So here is omega naught is 1 over RC. And why are we doing this? Well, we want to observe for some input to our system, we want to see what happens to it, whether it gets big, small, stays the same. And not only do we care about the magnitude, but we also care about the phase. And so why do we care about the phase of sinusoidal input? Well, one way we care about phase is if we consider something like an op-amp that amplifies the difference between the two terminals. If the phase is 180 degrees, well, let's see here. If the input to the positive terminal is sine of x and we're subtracting the opposite of sine of x, then that's 2 sine of x. And let's just say for simplicity that we're feeding back the output to this to this inverting terminal. Then the output keeps growing up and blows up to infinity. So we want to make sure that the phase shift is, when it hits 180, the gain is less than 1, such that this does not blow up to infinity. And another reason we care about the phase is, let's say we're feeding a square wave to our transfer function. Here, we know that by superposition, we can treat the input of the square wave as the sum of multiple different frequencies that make up the square wave. And if our phase response is proper, then we want to get the square wave at the output. But if our phase response changes with the frequency, then we might get all sorts of crap at the output instead. So here, let's look about how we actually write the magnitude and phase of our terms. So for a transfer function that's complex, we know the magnitude is the square root of the real part squared plus the imaginary part squared of the numerator over the square root of the real part squared plus imaginary part squared of the denominator. And the phase is the arctan of the imaginary over the real of the numerator minus the arctan of the imaginary over real of the denominator. So here, for the magnitude, our numerator is just 1, so that's going to be 1. Our denominator, real part squared, is just 1, plus imaginary part squared is just omega over omega c squared. So this is our magnitude. And let's look at our phase here. Our phase, since our numerator is just 1, the imaginary part is 0, and an arctan of 0 is just 0. So that'll be 0 minus imaginary part, omega over omega c, here, over 1. So that's what we're left with there. Now, if we inspect how the magnitude and phase change over frequency, we see that when omega equals omega c, we get 1 over the square root of 2, because this is 1. 1 over the square root of 1 plus 1 is 1 over the square root of 2. If omega is much less than omega c, we can ignore this term completely, and we have 1 over the square root of 1. If omega is much bigger than omega c, then we can ignore the 1, because this term is much greater than 1, and we're left with just omega c over omega as the magnitude. Similarly for the phase, if omega equals omega c, then if we look at this equation here, minus arctan of 1, well, the arctangent of 1 is just 45 degrees. So the opposite of 45 degrees is minus 45 degrees when omega is omega c. If omega is much less than omega c for the phase, this is minus arctan of 0, which is just 0. And if the omega is much greater than omega c, this number is very large. We see that arctangent approaches pi over 2 as the argument goes to infinity. And the reason we're using these simplifications here is because when we plot transfer functions, we typically use a log scale to take advantage of these. And if we're taking log scale for voltages, we usually use 20 times the log of the voltage. And so, for example, here, 20 log of 1 over square root of 2 when omega is omega c, that's minus 3. So you'll commonly hear the 3 dB point is actually this break point here where omega is omega c. And 20 times log of 1 over 10 was when omega is much greater than omega c. So we can simplify and ignore the 1 here. So if we take 20 times log of 1/10, that's actually minus 20. And if omega is 100 times omega c, we'll get 1 over 100. 20 log of 1 over 100 is minus 40. So the slope is minus 20 dBs per decade. So every time you multiply the frequency by 10, your magnitude decreases by 20 dBs. And here we'll look at the phase. We see when omega is much less than omega c, our phase is 0. When omega equals omega c, our phase is minus 45. And when omega is much, much greater than omega c, our phase is minus 90. Now, what if the circuit is really, really complicated like this? We'll have, these are all the different terms you could possibly have in a transfer function. A constant, some s over a constant, 1 plus s over a constant, and then these two, the reciprocal of those. I didn't put a constant in the denominator because that would just get absorbed into this. Now, by log rules, we know that we can treat each of these terms individually and sum up their results. So numerator, we add, something in the denominator, we subtract. And you can just take a screenshot of this. These are all the different rules possible. We see that for constants, you just take the 20 times log of that constant. There's no frequency dependence. So the phase is also 0 constantly. For something like this, where it's just s over a constant, see that when omega s equals omega c, this is just 1. Log of 1 is 0. And when s is omega c over 10, that's just minus 20. 20 times log of 1/10 is minus 20. And you can do the math and figure out why all these are the way they are. I'll just say the phase here for these constant, for the s over a constant, it's because we know that the phase is arctangent of the imaginary over the real. And if there's no real term here, it's just an imaginary term. Unlike here, where the real term is 1, that just goes to infinity. So the arctangent of infinity is 90. Arctangent of minus infinity is minus 90. And as an example, let's take something such as this band reject filter here. And that has a transfer function shown this way. And in this example, the designers thought it was advantageous to declare RC as tau, so they didn't want to have S over some omega when really all that matters is tau. But it just comes in handy to realize that the breakpoints here are going to happen at omega is 1 over tau, omega is 0.44 over tau, and omega is 4.56 over tau to fit the forms that we have here. And here's the transfer function rewritten, and as omega increases, these are the breakpoints we're going to observe. Here we have the constant term of 2, and 20 times log of 1/2 is minus 6, so that's why they've added this minus 6 dBs here. Let's see, when omega is 0.44 over tau, we're going to start decreasing by 20 dBs per decade based on the rules above here. And when omega is 1 over tau, we actually have 2 of these going to kick in at the same time. So instead of plus 20, we're going to have plus 40 because they are plus 20 dBs per decade at the same point. And when we get to 4.56 over tau, we're going to decrease because of this term here by 20 dBs per decade. And if you just line up all of these and start adding and subtracting, you'll get something that looks like this. And we can actually confirm that by using Matlab. So here's the function from before. Just plugged into Matlab. I defined tau as 1 over a million. And you can pause this and type this in if you want. But here's the function we actually get. We see it's quite close to the back of the hand calculation we did before by just summing and subtracting these individual terms. We see this kind of behavior for the final result where there's a little notch and it goes back up to 0 dB and the phase response looks like that with the hump. And if we expect at the bottom here about a frequency of 1,000,000, we see yes, 1 over tau is 1,000,000, as we said here. 0.44 over tau is where we expect this first breakpoint to occur, right from minus 6 dBs downwards. And let's see, 0.44 over tau is about 440,000. So this is 100,000, 2, 3, 400,000. And yeah, we see that's pretty much where that breakpoint starts to happen. Similarly, for 4.56 over tau, we want that to be the peak of the phase response, kind of where it starts to level back off to 0. And how I've defined tau, 4.56 over tau is about 4.5 million. So let's see, this is 1,000,000, 2, 3, 4 million. And yeah, we see that's pretty much the peak of the phase response and where it starts to curve back up to 0. So yeah, that's how you can use Matlab to confirm your back of the hand calculations. And lastly, I'll talk about gain and phase margin, which you'll hear about when talking about stability. And like I said before, when the gain, or when the phase hits 180 or minus 180, you want the gain to be less than 1 so that you don't get instability and your output doesn't go to infinity. So here we see when the gain crosses unity, we have our phase is not quite at minus 180. So the difference you have until you're out of luck is the phase margin here. And similarly, the gain margin is how much gain you could have had when the phase hits minus 180 or 180.